Welcome to the Explainer. Right now, an invisible war is raging inside our most advanced AI systems. And it's a conflict fought not with conventional weapons, but with altered pixels, manipulated datasets, and mathematical exploits. So today, we're going to expose the hidden vulnerabilities of the technologies we trust most by demystifying adversarial machine learning.
Here's our roadmap for this cat-and-mouse narrative. First, the threat of adversarial AI. Second, how these attacks actually work. Third, the real-world consequences. Fourth, defending the AI systems. And finally, the ongoing arms race.
Before we get into the technical weeds, I want you to consider a scenario. What if an invisible pixel could crash a self-driving car? We naturally tend to think of artificial intelligence as perfectly rational, cold, and mathematically sound, right? But what happens when the very statistical foundations that make AIs so powerful are deliberately weaponized against it? Well, as it turns out, perfection is just an illusion.
Section 1. The threat of adversarial AI. Okay, let's dive into this by exploring the foundational flaws hidden deep inside modern machine learning models.
To understand the threat, we first have to define the battlefield. Adversarial machine learning, or AML, is the study of malicious, often completely imperceptible manipulations of AI systems that aim to subvert their intended functionality. The crucial reality here is that these algorithms are incredibly good at learning intricate relationships from vast datasets, but the decision boundaries they learn are actually surprisingly brittle. We're talking about algorithmic manipulations that are entirely invisible to human observers but are absolutely catastrophic for the machines processing them.
Let's look at why this huge disconnect between human and machine perception exists. Human vision recognizes context, shape, and nuance. If you look at a stop sign with some graffiti or a few scratches on it, you still instantly recognize the context. It's a stop sign. AI vision, however, relies heavily on statistical correlations. It processes what data scientists call a high-dimensional feature space. So what looks like a tiny speck of meaningless noise to us can actually represent a massive calculated identity shift in that feature space for a neural network. It completely tricks the system into misclassifying the object.
Section 2. How adversarial attacks work. So, how do malicious actors actually pull this off mathematically? Let's break down the mechanisms of the attack.
Now, what's really interesting here is the stark difference in what an attacker actually needs to know to break an AI. In a white box attack, the attacker has complete knowledge of the target model, its architecture, its parameters, its gradients. They can use algorithms like the fast gradient sign method to calculate exactly which pixels to push and in which direction to maximize the model's error. But then you have black box attacks. This is wild. Hackers don't even need access to the AI's internal code. By relying on a phenomenon called transferability, where an adversarial example crafted for a public surrogate model magically works on an entirely different private target model, or by simply querying the target system to observe its confidence scores, attackers can craft devastating manipulations completely from the outside. We also need to distinguish the timeline of these attacks. Are we attacking the AI right now, or setting a trap for later? Evasion is about tricking the model during inference. This is dodging the AI's logic today by feeding it a manipulated image so it makes a mistake in real time. Poisoning, on the other hand, is a long con. It occurs during the training phase. The attacker injects malicious, corrupted data points into the training dataset to essentially plant hidden backdoors. It's exactly like planting a ticking time bomb deep within the AI's memory, just waiting for a specific, seemingly innocuous trigger to be activated weeks or months down the line. Section 3. The real-world consequences. The mathematics behind these vulnerabilities are absolutely fascinating, but to truly grasp why this matters, we need to ground this theory in reality across different domains.
We aren't just talking about minor software bugs here. We are looking at critical threats to physical infrastructure and human life. In the auto industry, placing subtly modified, mathematically calculated stickers on road signs can trick the computer vision of self-driving vehicles, potentially causing them to read a stop sign as a speed limit sign. In the military sector, adversarial noise can be deployed as digital camouflage, hiding physical assets from AI-powered surveillance drones, or worse, tricking targeting systems. And perhaps most terrifyingly, in the medical field, tiny adversarial perturbations applied to cancer MRI scans can completely alter an AI's diagnosis, leading to a missed tumor or a life-altering false positive.
And the scale of this vulnerability expands into almost every digital convenience we rely on. Take finance, for example. Adversaries are continuously exploring ways to craft imperceptible fraudulent transactions that slip right past AI-based fraud detection systems, leading to massive financial losses. Or consider natural language processing, or NLP.
By applying adversarial modifications to audio waveforms, attackers can manipulate voice assistants. So a sound that seems like random static to your ear, or even just the sound of a blender, could be perfectly interpreted by your smart speaker as a command to disable your security system and unlock your home's front door. Crazy, right?
Section 4. Defending the AI systems. The threat landscape clearly sounds grim, but the AI development community is fiercely fighting back. So the crucial point is, how do we protect these systems? One of the most studied and effective defense strategies developed so far is the adversarial training loop. I want you to think of this almost like an immunological response for a machine. Step 1, the developers purposefully generate their own adversarial examples to see what breaks the model. Step 2, they deliberately add these malicious examples to the training batch right alongside the clean data. And step 3, they update the model's parameters to correctly classify both. So by deliberately infecting the AI during its training phase, the system learns to recognize and resist these specific manipulations. It makes its decision boundaries far, far more robust.
But listen, adversarial training alone isn't a silver bullet. Defenders are forced to use layered security measures. First, there's input preprocessing. This involves techniques like compressing or denoising images before the AI even analyzes them. It essentially wipes away the attacker's subtle noise, like dirt off a windshield. Then there's building robust architectures. These are specifically designed using robust optimization, preparing the model for worst-case scenarios rather than just your average conditions. And finally, we have anomaly detection. Because adversarial examples often have statistical irregularities, defenders can build secondary auxiliary networks specifically designed to flag inputs that just don't mathematically look right before they can do any damage.
Section 5. The ongoing arms race. Even with these robust, layered defenses, the conflict is far from over. Let's look at the dynamic between attacker and defender.
And this brilliantly illustrates the overarching narrative of adversarial machine learning. It is a digital Cold War. On one side, you have the attacker, constantly probing for new brittleness in the AI's decision boundaries, finding novel ways to calculate gradients, extract model data, or exploit feature spaces. On the other side, you have the defender, continuously plugging these newly discovered holes with those layered defenses we talked about. And as soon as a new mathematical defense is published and implemented, attackers immediately begin evolving their tactics to circumvent it, pushing the boundaries of machine learning theory further every single day.
Which brings us to a profound philosophical realization prompted by the researchers of this field. High accuracy on a test dataset does not necessarily equate to true understanding or robust decision-making. Think about that. Just because an AI performs perfectly in a pristine, controlled lab environment, that absolutely doesn't mean it actually understands what it's looking at out in the messy real world. If a multi-million-dollar neural network can be entirely fooled by a few manipulated pixels that a human child would just ignore, well, its high performance is just an illusion of intelligence, leaving it entirely vulnerable to deliberate interference.
This leaves us with a critical, urgent imperative. As we rapidly integrate machine learning into our autonomous vehicles, our military defense networks, our hospitals, and our financial markets, as we essentially hand the keys of our physical and digital world over to AI, who is securing the AI? The future of artificial intelligence isn't just about making models smarter or faster, it's about making them trustworthy enough to survive in a deeply adversarial world. Thank you for joining me for this explainer. I really hope it changes the way you look at the complex systems quietly running our modern lives. Keep questioning the algorithms and keep learning.